Hello. This is Math 280 Multivariable Calculus. I'm Professor Wheatley. Our topic today will be differentiation in higher variables. So partial derivatives is what we're going to talk about. And the first thing to take note of is that when you differentiate a function of two variables, there is no more derivative. It's now a question of partial derivatives and directional derivatives, and which one do you want to consider? It's not just a single derivative anymore. There's not that case. So let's talk about partial derivatives. Let's start with the function f of xy. And what I want to do here is fix one variable. So I will fix completely arbitrarily y. So e.g., let's fix y. X range is free. And the idea here is by fixing a variable, the old standby example is growing a plant. If you have a plant and you measure height every day and you do two things to it. You give it a certain amount of water every day and, say, a certain amount of plant food every day. And you want to try to figure out what's causing it growth. If you change both plant food and water in a given day, it's hard to tell what's really causing the growth. Is it one or the other or a combination? But if you let the plant food stay fixed and only change the water, then you can really see what effect the water is having on it. In other words, is the water changing things? Is it making it grow more or less? The same thing if you just fix the plant food and or fix the water and vary the plant food. You can see truly what effect the plant food is having. You can isolate the rate of change. That's why when we talk about derivatives of functions of more than one variable, we have to keep something fixed, at least in the initial stages of things. So what do we have here? We have a bunch of points that look like this. They look like x0, y0, x1, y0, x2, y0, etc., etc. Notice I'm always fixing y and letting x be what it wants to be. It can go over the domain of the function from the x standpoint. Right? So I care about instantaneous rate of change of f with respect to x, so WRT with respect to x, at a point x0, y0. How do I get it? Look at average rates of change between, say, f of x0 and f of y0 and some points close by. So there's not much new here happening as h goes to 0. So just like with single variable calculus, how did I get the derivative, the rate of change at an instant? Well, I looked at rates of change of smaller and smaller time intervals. I found tangent line slope with secant line slopes of increasingly shorter and shorter secant lines. The rate of change at an instant came from average of change over an interval. Here, notice the y values are always the same. I'm only altering the x's, and I'm getting closer and closer to x0 on the x-axis. So this is nothing really new, i.e., the limit here under consideration is h goes to 0 of f of x0 plus h, comma y0, minus f of x0, comma y0 over h. Only x is changing here, not y. We are fixing y, right? So this is what is called a partial derivative. Partial derivative of f with respect to x at a point. Right? So that limit is the partial derivative of f with respect to x at the point x0, y0. Right? This limit here looks a lot like our single variable derivative definition, only there are two variables here, but one of them is remaining the same all the time. Doesn't matter. y0 is fixed. There are various notations here. We'll talk about them in a minute. One notation here is this f sub x. Right? So we used to use f prime and things like that. Now we use f sub x to indicate partial with respect to x. And f sub y would be with respect to y. Right? And in fact, we can say over here, there is a completely analogous definition for the partial with respect to y. It is just the limit h goes to 0, f of x naught, y naught plus h minus f of x naught, y naught over h. Let me erase some of this here. That is the partial derivative with respect to y. So this is a partial derivative with respect to y at a point that should be x naught. So here we're just varying y, fixing x. Nothing really that different at all. Notations here. So I said there were several notations, just like there are for derivatives. Depending on what you're doing, one may be more helpful than the other. Suppose that z is a function of x, y. Then I can talk about partial derivative with respect to x of x naught, y naught. Looks like that. I can use this symbol here, this partial f partial x of x naught, y naught, where this symbol is the partial differentiation operator. Right. Just like the ordinary d is the ordinary differentiation operator, this partial differentiation operator. It looks kind of like a d, but it's not. So don't mistake this for a d, and don't write d when you mean partial, or don't write partial when you mean d. To be somewhat careful, but this is a different notation than the usual d. It's sort of like a 2 without the finish to it, something like that. I can also write partial z partial x of x naught, y naught to mean what I say, z and f being the same thing. All right, so those are all derivatives, or all notations for the partial derivative with respect to x, right, or x's partial derivative. And the same thing works for y. I can write partial f partial y, partial z, partial y, like that. So again, alternate notations. These guys still leading to the idea that this derivative is a limit of a quotient. Okay. All right, how do I do it? What do I do? So if I'm faced with a question of actually differentiating a function partially, how do I do it? I differentiate my function f with respect to x, and I treat y as a constant. So really, from an analytical standpoint, what I'm doing process-wise is no different than what I said I was going to do when I did my definition. We'll see how this works. And certainly, if I change this to a partial y down here, I would reverse these variables, I would say, with respect to y, treating x as a constant. Let's try an example here. I think this is probably easier than you might think it even is. So let's try this function. How about x cubed plus x squared y cubed minus 2y squared? And I'd like to find f sub x of 2, 1. In other words, the partial with respect to x, the point 2, 1. How do I differentiate here? Well, I have to differentiate this function with respect to x, treating y like a constant. What does that mean? Well, this term, x cubed, is easy. It's just 3x squared. That's no problem. Then I come across a term that has both an x and a y. I have to treat y like a constant. So imagine for a minute that y was constant, and I had the function 8x squared, something like that. How do I differentiate it? Well, I just take the 2 down in front and drop it by 1, and I have 16x, right? Well, what happened to the 8? It hung around in the front, right? A constant hangs around when you differentiate. It doesn't go anywhere. It gets multiplied by whatever it needs to, but it doesn't leave. The same thing here. This y cubed is just like a constant. So this is more or less like constant times x squared. And if I have constant times x squared, my derivative is 2x times constant. Let me say that again. If I have constant times x squared, my derivative is 2x times constant. The constant here is y cubed, right? So this winds up being 2x y cubed, right? So this is derivative of x squared is 2x times the constant y cubed. And then the minus 2y squared piece, that's all a constant. It's like I had a minus 7. So if I take that thing's derivative, it's 0, right? Derivative of a constant is always 0. So this piece has no x term at all, and it's just a constant. It has 0 derivative. So this function is the partial derivative with respect to x. Right? Now my only question is 2, 1. I plug in 2, 1, right? That's 12. That's 4. I get 16. Okay? So there's an example of that. Excuse me. And let's try, how about f sub y of 2, 1? Same game. The x cubed term has no y in it. Nobody. It's a constant. A constant derivative is 0. It goes away. Here, this is like y cubed times a constant. So what is the derivative? The derivative is 3y squared times the constant. The constant is x squared. Right? And this is just a y piece here. That's easy. We know how to do that. That's minus 4y. Evaluated at, what do I want to do here? 2, 1, yeah. 2, 1, that's 4, and so that's 12. Minus 4 is 8. So these are not equal to each other, clearly. Right? And certainly, it's clear that these two functions are not equal to each other. So generally, fx not equal to fy. That's unusual if they are. That's generally true. OK. Let's look at another example here, maybe something slightly harder, but still not too bad. How about g of xy equals a y squared cosine xy. There, you have to have something inside of, so you have a chain rule situation going on here. Let's get the partials. Partial g, partial x. Well, I've got to use product rule and chain rule here. Both. I've got a product and a chain situation. So product rule works the same way. I mean, it's partial g, partial x of y squared times cosine xy plus y squared times partial g, partial x cosine xy, right? So this is product rule applied to that function, right? Product rule works exactly the same way as it does for ordinary derivatives. Okay? So now what? Well, partial g, partial x of y squared has no x terms, like a constant, right? Derivative is 0. So this whole thing becomes 0. How about over here? Partial g, partial x. This is like we have cosine 3x here, right? If we have cosine 3x, how does chain rule work? It's inside derivative times outside derivative, right? In other words, the derivative of cosine of 3x is 3 negative sine x, or negative 3 sine x. Same thing here, right? The derivative here is still a chain rule deal, right? It's still a minus sine xy times the inside guy's derivative. What is this inside guy's derivative? It's x constant, right? Its derivative is just constant, right? Its derivative is just constant, right? So we look like that. And then that whole thing times this y squared here. So again, This is like saying cosine 3x, right? Its derivative is going to be negative 3 sine sine 3x. This is playing the role of 3, right? This is playing the role of 3. There it is. There it is inside again. Everything else is the same. So this winds up being negative y cubed sine xy, like that. Right? So that's treated like a constant. How about partial g, partial y? Right? Same setup for product rule. Right? Same setup as above, only now we're doing partial g, partial y. The first part is easy. It's just a 2y cosine xy. The second part, got this y squared hanging around. Now the x is acting like a constant. Now it's like cosine 3y. So now the roles of x and y are just reversed, right? The x comes out as the constant, and you have a negative sine xy. So this ends up being minus x sine xy. And that is about as simple as it's going to get, is this expression here. So again, here the x was a constant. It came out, ended up with a sine of xy. Okay. So there are a couple of examples of how to do this. And it gets easier with practice, but always keep in mind, sometimes it's a good idea, I think, to even sort of on your side work, maybe if you're doing the partial g, partial x, to pretend like you're differentiating the function y squared cosine 3x, or 3 squared cosine 3x, right? Just plug in an actual value for x, right? And you can see that if you did this, right, this is 9 cosine 3x, and what happens here? So if I did d dx of this guy, right, I wind up with negative 27 sine 3x. And take a look. Y was 3. Look at this up here. This is negative 3 cubed sine 3x. So if you're sort of stuck, you can always pick a value for y. So say here, e.g., pick y equals 3, or whatever value you want, and then do it that way. I think this is a good way to do it early on, especially if you're having trouble with these kind of problems. Okay, geometry. Here goes. Let's draw a picture, and then we'll see what we can get from it. So here is space. Let me make some of these. So let's put, well, let me draw my surface on here first, and then we'll put some other things in here. So how about a surface that looks like that, and then maybe it's going like that, and there, and maybe you get something that looks like that. Yeah, that will work for me. And yeah, that's good. So there's the top of it, and then that's beneath, and then reasonably good. Okay, so there's a surface. So this is a graph of z equals f of x, y, some surface in space. Right? And so the red thing is z. And we know that a point on that surface, right, i.e. z naught equals f of x naught, y naught, means the point x naught, y naught, z naught is on the surface. Right, so maybe it's there. So there's your point. Right, there's your point. Okay, now, what do I want to do when I look at a partial derivative? I want to fix the value of one of the variables. So let's start by fixing y. Let's fix y equals y naught, right? So there's the y-axis. There's x, z, right? So this guy has, and actually, let me actually, here, we can extend this down slightly. Maybe there's the point x naught, y naught in in the xy plane. It's down there, right? So this is the value of y. This is y naught. Right, this is y naught. And I want to fix that value of y. I'd like to look at the curve. We'll call it C1, where the plane y equals y naught cuts the surface z. All right, so what I want to do is I want to run a plane perpendicular to the y-axis right up through the surface. So imagine a plane coming out of the y-axis and slicing through this surface, right? It's going to leave a curve of some sort. It's going to leave a curve of some sort. And maybe it looks something like that. Well, I've missed my point, but more or less I hit it. Well, that's pretty cruddy, but OK, that'll work. So there's the curve you get. So when I come up, so my surface exists. Here's my surface. It exists up here, all right? I'm coming up, and I'm slicing through it. Kind of make things work eventually. Slicing through it with a plane, right? And I'm making a curve. So this is a curve in the surface. Along that curve, every single y value is fixed. The only things that are varying are x and z, right? OK. And I can do the same thing for x. I can fix x equals x naught. I can look at the curve C2, where that plane cuts the surface. And so this is, let's see here. So that's x naught over there, maybe, right? I slice up with a curve, right? And I fix the, I have a plane that's now slicing perpendicular to x, right? It's slicing through this point and the surface and making some curve. And maybe we'll use, well, I don't want to use black yet. So maybe we'll use, or red. Maybe we'll use that. So there's another curve. Maybe it's C2, maybe. So there's C2. So there is some curve that this plane makes in the surface when it goes slicing through it. Right? And so now we can say to ourselves, well, what are the partial derivatives? Let me draw another picture here. When I isolate y equals y naught, I'm in the plane y equals y naught, right? So here in the plane y equals y naught, what's varying are x and z, right? And this is now a 2D curve. It's no longer something 3D. I made one of the variables fixed, right? So I can now say, well, what does my curve look like? It looks something like that, right? And maybe right there, maybe that's x naught, z naught, right? So this is a picture of what this curve looks like in the plane y equals y naught. And similarly, here's a picture. Let's just vary y and z, and let's look in the plane x equals x naught, right? This is C1 here. There, we get somebody that looks maybe like that, right? And maybe over there, there's y naught, z naught, C2, right? This is, again, a 2D thing in this plane. I can draw a tangent line to each of these 2D curves, right? If this was just y a function of z and x a function of z, and they are. When I fix one variable, this thing goes from being a 2-variable to being just a function of one variable. The other variable is just kind of there. It's not doing anything. I can do a tangent. There's a tangent. There's a tangent, right? I can call this tangent T1. I can call this guy T2, right? Those guys are up here as well. In other words, there's T1, there's T2 on my picture, right? They have slopes. Their slopes are the partial derivatives, right? So the partial derivative with respect to x of f at x naught, y naught is the slope of the tangent T1 to the curve C1 at x naught, y naught, z naught, right? In other words, I've drawn over here T1, I've drawn over there T1, right? The slope of this tangent T1 is the partial derivative with respect to x at that point, right? That curve's, or that line's slope is the partial. And similarly, f sub y is the slope of the tangent line T2 to a curve C2 at that point. And again, tangents has a slope. So the partials are just tangent line slopes. Tangent line slopes to two-dimensional curves that happen when I cut a surface with a plane, right? Because a plane cuts a surface in a curve. Okay, so there is some geometry to keep in mind, more or less. Even more than that, let me erase these over here. We can talk about rates of change and think about it in very direct terms. This partial with respect to x, right? This is rate of change of f just in the I direction. Right? Just in the I direction, because the j direction is fixed. There's no movement for y. This partial with respect to x is rate of change just in the I direction. Right? And similarly, partial with respect to y is rate of change in the j direction. So that's rate of change. And so these are not such unfamiliar objects to us. They're very similar to what we've seen before. Let me do an example here and maybe get rid of some of this stuff. So, example, here is a hyperbolic paraboloid, y squared minus x squared. What is fx of 1, 1? Well, numerically, this is easy. I mean, partial derivatives, this guy doesn't have an x in it. Its derivative is 0. It's gone. This guy is just minus 2x. So minus 2x at 1, 1. Y has no bearing on things. It's minus 2, right? What does this mean geometrically? If I fix y to be 1, I'm looking at the plane y equals 1, cutting this paraboloid, right? This plane cuts this surface. What does it cut it in? A 2D curve. It intersects the surface y squared minus x squared in a parabola, right? Because think about it, if I plug in 1 here, I get z equals 1 squared minus x squared, right? In particular, I get the parabola z equals a negative x squared plus 1. When x is 1, right? When x is 1, the tangent line has slope negative 2. This is negative x squared plus 1 in the xz plane, right? There's the tangent line with its slope, right? Slope of the tangent line to this parabola is minus 2. So slope of tangent to this parabola at the point 1, 1, 0. And actually, I'm sort of being silly up here, putting my point in the wrong place. That's where it should be, like that, 1, 1, 0, because when I plug in 1, 1, I get z equals 0. That's where my tangent line should be, is minus 2. Okay, so here's a real chance to see directly when I cut with this thing with this plane, I get this object, and that's a tangent slope. And similarly, if I look at f sub y of 1, 1, Again, life is pretty easy. It's just 2y, because this is 0. So at 1, 1, you get positive 2. How does the game work now? Plane x equals 1 intersects the surface y squared minus x squared. This time intersects it in a parabola x squared, or I'm sorry, a y squared minus 1. Y squared minus 1. How does the picture look now? There's y, there's z, right? Now it's an upward opening parabola, right? So now you're here. Look at your tangent line slope. It's positive, positive 2, right? So slope of tangent to this parabola, which is now upward opening, at 1, 1, 0 is positive 2. Okay? So you can see this is, I think this really illustrates the geometry of what's happening with these partial derivatives. All right, let's try a problem with implicit differentiation. It turns out, actually, we'll be able to make this somewhat more systematic down the road, but for right now, the good news is things work more or less the same. We can apply the same tricks that we did in Calc 1, so if it went well then, it should go well now. So maybe we have this function x cubed plus y cubed plus z cubed plus 6xyz equals 1, and I am assuming z is implicitly defined as a function of x and y. Not explicitly defined. I can't solve for z, but it is implicitly defined. Right? I'd like to find partial z partial x. How do I do it? Well, I take partial x of both sides. Right? Partial z partial x. Take partial x of both sides. Let's see what I get. First thing is easy. Right? I get 3x squared. Derivative with respect to x of y cubed is 0, because y doesn't have an x term in it. It's constant. It's gone. This z cubed, right, I have to say to myself, well, I'm not quite sure what's going on with that, so let's leave that for the time being. Z cubed, like that. So we'll leave that for the time being. And then we also have this other kind of ugly piece that involves x, y, and a z, and then equal to 0, because partial x of 1 is 0. So these guys are the guys in question, right? And we handle these guys just like we handled implicitly defined functions in Calc 1. Z is a function of x and y, so we have to resort to the chain rule, right? And the chain rule says that it's derivative of the inside times derivative of the outside, right? Well, derivative of the outside here, the outside is the cubing function, right? So the outside gives us this 3z squared, and the inside is this. I mean, what is partial x of this? Well, it's just partial f, or I guess I'm using z here, aren't I? It's just partial z, partial x, right? This could be some function of x and y, I don't know, or a function of one or the other. I take its partial, I get just this. It's just like when I differentiated y equals f of x, I got a y prime out, right? This is the piece I want to get out of this, right? And then this other guy, he's even more sort of troublesome because he's a product. He's a product of things involving x and y and something involving z. So I'm going to be a little careful here. I've got to use product rule. So I'm going to break it up into the pieces that involve just x and y and the pieces that involve z. Right, so here I've broken it up. Here's a piece 6xy. Here's a piece z, which is a function of x and y. I don't know what this is. Maybe this is cosine of x squared plus y squared. I don't know. But it's some piece involving x and y. I had to use product rule, right? This is a product of two things. Now I can handle this straightforwardly. Right? Everybody else just gets dragged along for the ride. Partial x of 6xy, it's like having a constant here, and the 6 is already a constant, so this is just a linear term of x. This is x times the constant 6y. The constant 6y lingers. The z comes along. Here it is. Over here, what's another way of saying partial x of z? Partial z partial x. All right, partial z partial x. And again, my goal here was get these partial z partial x terms. I want to solve for this. I want to get this isolated. How can I do that? So I can move some things over and get some things isolated here. So partial z partial x, 3z squared plus 6xy equals minus 3x squared minus 6yz. Right, scoop these guys over, factor that out. And then I can just divide, and I can pull out, I believe, a 3 here. Anything else I can pull out? No, just a 3. Actually, I can pull out a negative 3, can't I? And that'll give me in the top an x squared plus a 2yz. Divide out, pull out a negative 3 there and a negative 3 there, and I do get minus z squared minus 2xy. And is that what I have? Yes, yes, it is. So here's what you get when you solve all of that. So the process is the same as it was before. We treat z terms like this, and we use chain rule. We attack the outside with z's and attack the inside with partials. And again, we'll see a little bit more about this down the road, how to make this a little more systematic. But that'll take the chain rule in multiple variables to get that, so we don't have that yet. OK, that's implicit. How about higher order partial derivatives? So second order, third order. Just like there's second derivatives and third derivatives and et cetera, there are higher order partials, second order partials. All right, so this notation, it's a little, I guess, awkward in a way because you have the actual number 2 and this partial operator sign, which can look very much alike if you're not careful with your notation. This is the second order partial of f with respect to x. And this is also denoted or denoted f sub xx, right? So x once and x again, right? So this is f differentiated with respect to x twice. In other words, you go x once, then x again. But there are more possibilities in this. I mean, there was one second derivative. Here, I could go x first, then x again. I could go x first, then y. I could go y first, then x, or y first, then y again. There's 4 possible combinations of things going on here. So I could also have this notation here. I could have f sub y, which is y twice, y once, then y again. Or you could have some mixed partials. You could have partial x, partial y, right? F sub yx, right? And you could also have partial y, partial x, which is f sub xy. Excuse me. And this guy here is, again, it's not literally multiplication of operators, but take a look and see. It is the partial with respect to x of the partial with respect to y, right? I.e., differentiate y first, then x, right? Because this is taking partial x of a partial with respect to y. So partial x of a partial with respect to y. Same thing over here. This is partial y of a partial with respect to x, right? This is x first, then y. So what is irritating, I guess is the right word about this, is that via the Leibniz notation, we are reading right to left. We go y first, then x, right? Via the notation, which is sort of more anglicized, we read left to right, right? We go y first, then x. So sort of be cognizant. If you have this notation, think of it in this term. I mean, you're always applying from left to right. If this notation is literally reading across, it's like composition. When you have F composed with G, well, actually, I guess it's the reverse of composition, so ignore that comment. But so you read from left to right here. But here, this is like composition. You go outwards. You do this first, then that. So just be aware of what's happening. And these are called the mixed second-order partials. They are second-order partials that are one, then the other. These are just straight second-order partials. These are not mixed, just the same variable twice. All right, let's try an example here. Let me get rid of some of this. Let's see if we can't do some second-order partials. Here is a function, f of x, y, x times sine y plus y e to the x. Let's compute the second-order partials. This should be a fairly quick process. F of x, x, partial x on the partial with respect to x. So what is this guy's partial with respect to x? It is sine y, because this is just like x with a constant term. It's a linear term in x. And then over here, this is e to the x times a constant. Right? The sine y piece has no x's in it. It's gone. It's 0. We're just stuck with y e to the x, like that. F sub y partial y of this thing. Right? Oopsies, I'm writing the wrong thing. I'm botching this up. Don't write that. So what is this thing's partial with respect to y? Well, sine y's derivative is cosine y. The x is just a constant. It comes along for the ride. So this is x cosine y, right? This is a linear term in y. It's y times coefficient e to the x. So we just get e to the x over here. Do partial with respect to y of this. What do you get? You get minus x sine y, because again, this guy has no y in it. It's gone when you differentiate with respect to y. So these guys are not equal, clearly. Right? They're not equal. How about the mixed partials? The mixed partials say I do partial y first, then partial x. Well, this is partial x of x cosine y plus e to the x, right? This guy is partial f, partial y, same thing as this up here. Now I'm doing partial x of it, though. So again, this is linear in x, so what do I get? Cosine y, e to the x lingers, just an x term. How about f xy? This is partial y of partial f, partial x. Right? So now it's partial y. These look too much like 2's. Partial y of this guy. This guy is partial f, partial x. Right? Partial y of this. Look what happens. That turns into a cosine y. This is linear in y. Lo and behold, these guys are equal. These guys are equal. So what we see here is that the second order partials are equal. Coincidence? No. We have Clairaut's theorem. Which says this: if your mixed second-order partials are continuous in an open ball, and we're not going to get too specific here, but in a region around a point, in other words, not just at a point, but in some region around it too, then they are equal at that point. In other words, Clairaut's theorem says as long as your partials, your second-order partials are continuous at a point and nearby, then you're going to have the mixed second-order partials be equal. So for most of our functions, these are going to be equal. It's not going to be a big surprise. And in fact, it turns out that Clairaut's theorem extends to higher order derivatives too. In other words, if we take a third-order partial, it doesn't matter what order we stick these variables down there. As long as we have continuity, things are good. So let's try an example of that. How about f sub xxy? And the function in question is going to be y squared x cubed plus natural log x squared y squared. Y squared x cubed plus natural log x squared y squared. Okay. So we're going x first, then x again, then y. So fx of this thing is 3y squared x squared, right? Y squared is a constant. Over here we need chain rule, right? So I've got 1 over x squared y squared, and then internally there, the derivative of that thing with respect to x is 2y squared x, right? So that makes something a little neater. The y squareds will cancel because this is a domain restriction anyway. You can't have 0 on this side of this thing. And an x cancels, so we're left with just a 2 over x. That is f sub x, right? The first partial. And what have I, let's see here. What am I unhappy about? Nothing. Good. All right. So now let's do f of xx. What happens now? Well, I'm going x again on this guy, right? Going x again. So this is 6y squared x. This is 2x to the negative 1. So this is really minus 2 over x squared, like that. Minus 2 over x squared, right? And now we have to do y to this thing. So now we're at our third stage, fxxy. We do y to this. Now we have 12xy. This guy has got no y's in it. It's a 0. It goes away. 12xy. It turns out that this is equal to, if you did xyx, or if you did yxx, they're all the same. So as long as you have two x's and a y, this is going to be equivalent as long as we have continuity. And this guy has continuity on its domain, which is everywhere except for along the x and y axes, in which case this would be 0. Can't have that inside a natural log. So I have continuity, which is everywhere but x equals 0 and y equals 0. Notice, though, it's two x's and a y. it's not necessarily true, for example, and it's not true in this case, that if I did 2 y's and an x, I would get 12x. It matters about, I mean, it doesn't matter about the order, but it does matter about the content. In other words, if there's 7 x's and 5 y's in a 12th derivative, you can't mix and match them up. Any order of those is fine, but it won't be the same as 6 x's and 6 y's. It's not the same there. So that's an example there. Something brief to say here about second-order partials. We know that the second derivative in a single variable function talks about concavity. It gives the rate of change of the rate of change. A very similar kind of thing for a second-order partial. So suppose we had the second-order partial with respect to x twice, so fxx, right? This is rate of change of the tangent slope to that curve formed by the intersection of the surface f of x, y, and the plane y equals y naught at x naught, y naught, z naught. So it's the rate of change of the tangent slope to that curve. And remember that when I cut my surface with a plane, I got a curve, a 2D curve, right? I had partial f, partial x once. I fixed y, so I chopped up with a y plane, got a curve in the xz plane, or in a plane parallel to xz. That curve had a tangent line slope. That tangent line slope has a rate of change as I move along for different x values, right? Just like it does in a single variable case. And so if it turns out that this second order partial is greater than 0, for example, that means that the rate of change is greater than 0, which means an increasing thing. The tangent slopes are increasing at that point. Right? This implies that the surface is concave up, at least in the I direction. Right? So in other words, if your f sub xx is bigger than 0, your tangent slopes are increasing. At that point, the surface is concave up in the I direction, the direction of x. All right? And the same thing is true if I look at f sub yy, right? Then if I have that bigger than 0, the surface is concave up in the j direction, right? And if this guy is smaller than 0, it's less than 0, then the surface is concave down in the I direction. So the same idea as we had for single variable calculus, the second order partials tell us, at least in some way, about the concavity of our function in a given direction, at least. So you can be concave up in one direction and concave down in the other direction. You can have something like a hyperbolic paraboloid that meets exactly those criteria. Okay, so there's some discussion about that, right? The same ideas apply for f sub yy in the j direction. That's true. A brief word on functions of more than 2 variables. Everything works the same. Functions of 3+ variables. Everybody works the same. Isolate everybody except for the variable in question. Here's a function of 3 variables, 2z plus cosine x plus y squared plus z. That is a function of 3 variables. It is in 4 dimensions. If I want to know about the partials, If I ask for, say, partial f, partial x, I isolate both y and z. I treat both y and z as a constant. So for example, this term is a constant with respect to x. It's junk. These guys are constants. Y squared and z are both constants. So it's like cosine of x plus some constant. So this winds up being minus sine x plus y squared plus z. Because the chain rule has nothing to say here. I mean, the chain rule says outside derivative, that's this guy, times inside derivative. Well, inside partial with respect to x is just 1. There's nothing on the x except for a 1. Right? How about partial f, partial y? This is still constant. The difference now is we still have this outside piece, but now the inside derivative is a 2y. So we have that. So we have minus 2y sine that thing. That's equals. And partial f, partial z, this term now matters. It's 2. Everything else stays the same. There's nothing on the z term to make it have an extra derivative outside. So it looks like that. So very much like partial f, partial x, only with an extra 2. Again, we held x and y constant here and only looked at z changing. So these guys are easy. Everything follows the same techniques and things like that. OK, so one more thing to discuss in terms of derivatives. We need to talk about what it means for a function of two variables to be differentiable. It is slightly more complicated than it was in the single variable case. And we can use the following sort of counterexample to motivate us here. So differentiability. In single variable calculus, if you had a derivative, you were continuous. In other words, differentiability implied continuity. It turns out that if you just having partial derivatives at a point isn't enough to be continuous there. That's not enough. So let's look at an example here a minute. And this is one of these sort of degenerate functions, but it does serve its purpose in that it goes to show we need something stronger for differentiability. So here is a piecewise function. Drawing this guy is slightly difficult. So let me, OK, so there's the z-axis. So how do I want to do this here? All right, so there is the point 1 along the paths when x and y are 0. I'm sorry, not x and y are 0. Their product is 0, which happens along the x-axis and the y-axis, right? And so then down below that, let's see if we can make this look decent here. So there's the actual x and y axis. All right, and I should have drawn the z-axis in black too, yes. There we go. All right, let's get this. All right, so I want that to be, OK, that's better. OK, so what we have here is everybody who's not on these black dashed lines. This is down on the xy plane, right? The orange is a unit above, right? So the xy plane is in my hand. The orange is up here, right? Unit above. The orange sits above, directly above the xy axes. Everybody over here has value 0, right? Everybody not on one of these axes has functional value 0. Everybody on the axes have functional value 1. So that's this function here. Okay, this is the graph of f. OK, some points here. First of all, this function is absolutely not continuous at 0, 0, and it should make some sense. I mean, just think about it. Here's 0, 0. You're walking along the xy plane. Your value is 0, and then all of a sudden you leap to 1. So it should make some sense that it's not continuous. but it doesn't exist. It's very easy to see that if you walk along the path y equals x, the limit is 0. If you walk along the path y equals 0, the limit is 1. So two different pathways that approach 0, 0. One of them has limit 0. One of them is down here in the xy plane, and it's down here. One of them is entirely along this orange weather vane, so doesn't exist, clearly not. Therefore, if there's no limit there, that's one way for f to not be continuous. Because f is defined at 0, 0, but there's no limit, so not continuous. OK, but it turns out this function has partials that exist at 0, 0. Let me talk about that a minute here. So it's not continuous there, but let me talk about the partials over here. So what about partial f partial x at 0, 0? What does it mean? It means you fix y equals 0, and you have the following limit. You look at the limit, h goes to 0, f of 0 plus h, f of 0 plus h comma 0, f of 0 plus h comma 0 minus f of 0, 0 all over h, right? F of 0 plus h comma 0, well, as soon as that y value is 0, function value is 1. This function value is 1. So this ends up being the limit h goes to 0 of 0 over h, right? That is 0. So the partial derivative at 0, 0 with respect to x is 0. And you can do the exact same process, only reversing the variables, to show that the partial derivative at 0, 0 with respect to y is also 0, right? So this guy is a funky function that has partials defined at 0, 0, but it's not continuous there. Now, what we want is we still want differentiability to imply continuity. This function says we've got to have a stronger condition for differentiability than just partials exist. We need something better. So having the partials exist is not enough. We need to have actually continuity of those partials nearby a point. So we need the continuity of fx and fy throughout an open ball containing x naught, y naught, in order to have f of xy differentiable at x naught, y naught. So we can't just have partials sitting there. We've got to have the partials, and they've got to be continuous. So for example, the point 0, 0, here it is in the xy plane, some open ball. It could be very tiny, but I must have partials that are continuous throughout some open ball around that point. And I will show that we don't have that. So we want to show that, for example, partial f partial x is absolutely not continuous in any open ball containing 0, 0. Right? I want to show partial f partial x is not continuous in any open ball containing 0, 0. Okay? Well, how do I show something's not continuous? I either show it's not defined, or its limit doesn't exist, or else limit exists and doesn't equal the point. Well, it turns out that the partials certainly exist here, right? So fx of 0, 0 is 0, so it's defined. So fx defined at 0, 0. Defined at 0, 0, like that, right? Well, any open ball around 0, 0, any open ball around 0, 0, it contains points on the x-axis, right? In other words, you can't be an open ball around 0, 0 without hitting the x-axis. It's not possible, right? And this is the path y equals 0, right? I'm sorry, I wanted to say the y-axis. The x-axis works too, but the y-axis. X-axis will work for the other derivative, but the y-axis, the path x equals 0. So any open ball contains points on both axes, but it contains points on the y-axis. Right? Now, let's consider approaching the point 0, 0 along this path. So let's approach 0, 0 along the path x equals 0. That's the y-axis, i.e. your points all look like 0, y0, where y0 is not 0. Right? So you're on points that look like that. And let's fix a point. Fix a point 0, y0. Okay. Let's consider the partial derivative with respect to x at that point. So where are we now? Redraw the picture. Here's 0, 0. Here's an open ball. I'm at some point within that open ball. I'm here. Right now I'm asking, so I'm there in the open ball. I'm asking what is the partial with respect to x at that point? Not 0, 0, but some other point on the y-axis. Okay, here goes. So it's the limit h goes to 0, f of 0 plus h, comma y0 minus f of 0, y0, all over h. Now, notice, y0 is not 0 anymore. This coordinate is not 0. It's 0 plus h. Therefore, this is some non-zero x and some non-zero y. Its product is going to be non-zero, means its functional value is 1. The point 0, y0 has product of x and y being 0. So this is 1 minus 0 over h, which is the limit h goes to 0, 1 over h. What happens to that? H goes to 0. This thing inflates. We get infinity, right? So the bottom line, along the path x equals 0, the partial with respect to x does not exist except at 0, 0. It's the only place along that path that it exists. There is no other existence of the partials along there, right? So therefore, any open ball contains points along the y-axis, right? The partial with respect to x doesn't exist there. Therefore, there's no way the partial can possibly be continuous in an open ball, right? Okay, what does that mean to us? That means that this function is not differentiable, right? It has partials there, but not differentiable. The fact is, if f is differentiable, at x0, y0, then it's continuous. We want that to be true. And it's this added restriction of continuity of the partials that gives us that result. And differentiability means what it meant in Calc 1. It means that there's a good tangent there. Not a tangent line now, but a tangent plane. Think about it. If I'm sitting on that surface at 0, 0, so here's the xy plane, here's my weather vane up here, sitting like that, right? If I'm sitting at 0, 0, and I move away from 0, 0, if I alter just x a little bit, I'm still on the weather vane. Things look fine. Looks like I'm still in good shape, right? If I alter just y a little bit, I'm still on the weather vane, right? I've moved away, but I'm still on that surface up here. If I alter both even the slightest bit at the same time, though, I drop suddenly down to the plane. So I fall off the marker down here, right? That means that that sudden drop implies I can't fit a tangent plane to it very well, to this surface. Nothing's going to work there. I'm going to wind up with not differential, which is what I have here. Okay, that's it.